My name is Eric Bogatin. I'm a signal integrity evangelist with Teledyne LeCroy. In this brief video, I'm going to walk you through some of the important features in the WavePulsar 40iX that dramatically simplify de-embedding. And this is part of the deep toolbox available in the 40iX. One of the important innovations that the WavePulsar 40iX has introduced is 3 integrated measurement and analysis modes, all in one instrument and all with one user interface. In other videos, I've walked through how we can use the WavePulsar 40iX to measure the time domain performance of various interconnects. And we can take that time domain performance and display it in a variety of ways. For example, as the TDR response from each of the 4 ports that are connected to the device under test. Or we can look at the through transmitted signal. Or, depending on the connections, we can also interpret some of the time domain measurements in terms of crosstalk. And whenever we have time domain measurements, we can use that information in order to give us spatial information of where discontinuities or other features are located. And when we take the single-ended response and turn it into the mixed mode response, then we can look at the differential TDR response, either the reflected or the transmitted signals, as well as the common signal response and even the mode conversion terms. In addition, in the same instrument, we can also collect the frequency domain response, which are really the S parameters. We can get the S parameters as single-ended S parameters up to 4 ports, or we can convert the single-ended S parameters into the mixed mode S parameters to look at what are sometimes referred to as the differential S parameters, but of course we also can display the common signal components and again the mode conversion terms. And one of the important features built into the WavePulsar 40iX is the ability to take those measurements and correct them for causality, passivity, and reciprocity so that we deliver simulation-ready S parameters. In addition to performing the measurements and doing the display, we can also import other touchstone files and display them along with the measured results, either in the frequency domain or the time domain. Well, the third important feature in the WavePulsar 40iX is a very deep toolbox that allows us to do important analysis of those fundamental measurements, whether displayed in the time domain or displayed in the frequency domain. In this brief video, I'm going to walk you through a couple of really important features that dramatically simplify the process of de-embedding and also being able to change the port impedance so that we can look at structures that are uniform but not 50 ohms. Let's take a look at the de-embedding problem and what we're trying to achieve and how we do it and how we use some of the features built into the WavePulsar 40iX to dramatically simplify this process. Here's the challenge that we've got. We want to get the S parameters of just the device under test that we care about. Unfortunately, in order to connect that device under test to the nice coax cables of the WavePulsar 40iX, we need an adapter. We call those adapters fixtures. We need to have a fixture that connects between the nice coaxial connector and whatever that device under test is, for example, if it's a trace on a circuit board. And of course, a fixture on the other side. What we end up measuring then is this composite structure. It's got the fixtures on the ends and the device embedded in the middle. An example is shown here of a simple microstrip trace on a board, may of course on the bottom side of the board that we can't see in this picture. The challenge that we have is we don't want all those fixtures in the way, we want just the device under test. How do we separate out just the device under test when we measure it embedded in these fixtures? That's where the magic of de-embedding comes in. And here's how it works, a little bit looking under the hood. Here is that composite structure that we start with. This is the measurement of the system of the device under test with the fixtures on either side. If somehow magically we could get the S parameters for the fixture on the left-hand side and the fixture on the right-hand side, if we could get those S parameters of just the fixture, then we can do a little bit of matrix math to de-embed just the device that we care about out of the way. And the secret to do that is we convert the S parameters that we've got, the S parameter of the fixture on the left, the X parameters of the fixture on the right, and that composite structure, We convert those 3 different S parameter files into what are sometimes referred to as T parameters or transmission parameters. And to do that, it's just algebra. I'm not going to go through the details of it. Here's what it really looks like. We take the S parameters of each one of these, we turn the crank, and we get the T parameters for each one of these 3 sets of measurements. When we look at the composite structure in terms of the T parameters, we really want to think of that as there's the T parameters for the fixture on the left, the T parameters for the fixture on the right, and the T parameters for the device under test. This is what we really want to get. And here's how we do it. The composite structure, that measurement of the composite structure that we've got, when we convert that one measurement into the T parameters, it's really composed of the T parameters of the fixture on the left times the T parameters of the device times the T parameters of the fixture on the right. Well, if we have these T parameters of this fixture and this fixture, through matrix math, we create the inverse matrix of that, and we literally multiply that on either side to the composite structure, and the fixture T parameters cancel out, and what we have left is just the T parameters of the device under test that we care about. This is the essence of de-embedding. Once we have the T parameters of just the device under test, then we go back and convert those into their S parameters, and now we've got what we want. We have the S parameters of just the device under test. The secret of doing this kind of de-embedding, which is just matrix math down here, the secret of making this possible is having the S parameters of the fixture on the left side and the S parameters of the fixture on the right side. That's the essence of doing de-embedding. Now, if this seems complicated, don't worry about it. And unfortunately, I have to say that this is the simplified version for the general public. It doesn't get any simpler than this. But don't worry, because all of this takes place under the hood with one mouse click in our deep toolbox. The secret, of course, is getting the S parameters for the fixture on the left and the fixture on the right. And that's where we take advantage of a really cool feature built into the deep toolbox of the WavePulsar 40iX. LeCroy pioneered this technique more than 10 years ago in our early Spark product, and it has since become adopted in the industry and goes by a couple different names. Some folks refer to it as in situ de-embedding. The IEEE P370 Standards Committee refers to it as impedance-corrected 2x through de-embedding. Both of these techniques refer to exactly the same thing. Here's the technique that we use in order to simplify de-embedding. The first starting place is we have to take the composite structure of the device with the fixtures on the ends, and we have to figure out where does the fixture end and the device under test begin. There are 2 ways we get that measurement of where the end of the fixture is. In the first method, we literally look at the TDR response. We look to see, given the features of the impedance profile, where is the end of the fixture and where does the device under test begin? And we do that on the left side and we do that on the right side. We look to see how far in from the beginning of the measurement does the fixture end and the device under test begin. And we make a rough estimate from the TDR response. That's one way of getting that point where the fixture ends and the device under test begins. The second method is possible if we have another structure that we've built that is a 2x through. That is just the piece of the fixture on the left and the piece of fixture on the right that's butted together as one extra fixture. We call that a 2x through. And in another video, I'll walk you through how we use a 2x through in order to find where does the fixture end and the device under test begin. Once we have that point, once we know here's the end of the fixture, here's the beginning of the device under test, we want to create a model for that fixture. And the way we do that is we calculate the impedance profile of the fixture from the TDR response. We calculate that impedance profile and we peel out, we extract out a transmission line model of that fixture. We build a series of short transmission line segments, each with different characteristic impedance and time delay that matches the impedance profile of the fixture that we've got connected on either side of the device under test. We sometimes refer to this technique as peeling the impedance profile. It's really translating that impedance profile into an equivalent transmission line circuit. Now that we've got that circuit and we know this behavior of the fixture can be described as this transmission line circuit, we can now take that transmission line circuit, calculate the S parameters for it, and now we've got the S parameters for the fixture. And once we have the S parameters for the fixture, we do just like we did before. We turn them into T parameters, we invert them, multiply by the T parameters of this whole thing, take the remaining T parameters of the device, convert that back to S parameters, and that's what we display. And all of that happens under the hood with one button push. Let's take a look at how we do that. So we're going to use as an example, I've got this board. This is a board that Don DeGroat and I developed a number of years ago for a class we were teaching on hands-on wave pulsar measurements. And it's got a variety of structures on it. In particular, we're going to take a look at this structure over here, which is not a 50 ohm transmission line. It's an extra wide line because I want to demonstrate two important features. The first is we're going to de-embed the fixture, which is the SMA launch, into that board. And the second thing we're going to do is once we're done, we're going to have a transmission line that's not 50 ohms. It's closer to 35 ohms. But yet we're going to see the S parameters in the 50 ohm environment. And I'm going to show you how we can renormalize the port impedances to look at how would that 35 ohm transmission line look in a 35 ohm environment. So let's take a look at the measurements. So we're going to go over to my lab and we're going to look at the board and how we do some of these measurements. Here we are in my lab, and you can see we've got the Wave Pulsar 40IX over here. We're just going to do a 2-port measurement on it. We have it connected to our test board, and here's our structure that's a little extra wide line with the SMAs going into the circuit board. And you can see right above the Wave Pulsar, here's this baby brother. This is our T3 TDR. That is just a 2-port differential TDR. It's a great instrument if all you care about is looking at the either single-ended or differential TDR response. If you want a lot more, that's where the Wave Pulsar 40IX comes in. It's sort of a TDR on steroids. So we've got the cables hooked up. Remember, when we use the Wave Pulsar 40IX, there's a built-in eCal unit inside the box, and so when we turn it on, it goes through a calibration and automatically brings the reference port to the beginning of the connectors on the front of the box. And then we have the S parameters for the cables. They're all serialized. We've got those measurements that are built into the EEPROM of the Wave Pulsar 40IX. And we de-embed from every measurement the S parameters of the cable, and so we have automatically moved the reference plane of the measurement to the end of the cable. And so in that way, literally out of the box, we have a calibrated measurement right to the end where the cable connects to the SMA on the device under test. Now we're ready to perform the measurements. When the Wave Pulsar 40X software comes up, we see displayed whatever was the previous measurement that we were doing. We're going to set up and perform a new measurement for this particular device under test, which is our 4-inch long line. We're going to use all the default cases, 40 gigahertz, 8,000 points, so we'll have 5 megahertz steps. We're going to enforce passivity, reciprocity, causality. We'll keep the impulse limit to 5 nanoseconds because we've got a very short structure. We've got 2 ports. It's going to be 50 ohm port impedance for now, and then we'll change that. Everything else is going to be the default case. We're going to make sure that gating is turned off for now, and we're ready to take our data. So I'm going to push go. We'll take the data, and of course, before we push that button, we want to anticipate what we expect to see. Remember, this structure that we're looking at is a relatively short interconnect. It's a 4-inch long trace. We've got the cables connected. We're going to see the discontinuity of the SMA launch into the board, and it's going to look like a low impedance. And so we're going to see ripples in the return loss quite a bit because number one, we have the discontinuity at the ends, and number two, it's not a 50 ohm line. And we'll see the signal coming through. We'll also display that data in the frequency domain and the time domain. And I like setting up my screen so I can see both sets of data at the same time. It's part of the value of having the integrated capability of displaying the information as S parameters in the frequency domain and in the time domain as the TDR response. So on the left-hand side, I like to display the frequency domain response, insertion loss, and return loss. And on the right-hand side, we'll look at the TDR response. So let's push go and see how well it matches our expectation. So remember, in the time domain response, I think we'll see a uniform trace in the order of about 35 ohms, and we ought to see a lot of ripple in the return loss and probably some ripple in the insertion loss. So let's take a look. And here is the result. And so you can see that we've got plotted here the return loss and the insertion loss. And sure enough, as we expected, there's a lot of ripple. Here's minus 10 dB. It's already starting out at the low frequency at a pretty large return loss. And because we're above that minus 13 dB point, we're going to see the impact of the ripples in the insertion loss. And sure enough, we do very strongly. Now, because of the SMA connectors I have on this board, they're going to have a cutoff frequency around the 18 gigahertz kind of frequency range, and you can see that we're dropping off pretty rapidly over here at here's 20 gigahertz over here at this point. Some of this is the monotonic drop-off because of the losses in the line, and some of this is that sharp drop-off because of the waveguide cutoff frequency of these particular SMAs. And sure enough, in the time domain, we see the launch discontinuity over here, and we see a relatively uniform transmission line, roughly around the 35-34 ohm range. The first thing we're going to do is de-embed the launch. And you can see the launch discontinuity. Here's this big discontinuity right here. This is the connector and the pads associated with the connector at that launch. So we want to eliminate this whole front piece of the launch. That's the fixture. Where is that? I want to know how far and how many picoseconds in from the edge is that launch. And we can literally read it off the front screen using cursors. So we'll turn on our cursors. We'll set it up so we're looking in the seconds or the time domain, which it is. It's all set for us. Here they are. And now we want to know how far in from the edge is the end of that fixture. Now, this is where we can adjust the scale that we use for the TDR response. When I look at the TDR response, I usually want to display the round trip time, the total time down and back. And I set up in the TDR response, I set up for display the round trip time. But this is one of those cases that I'll save myself a divide by 2 operation, and I'll say, just give me the one-way time delay display. So it will literally take that round trip time and divide it by 2. So we'll apply that. And now when I move the cursor around, if we look down here where the time delay of the cursor is from 0, so if we move it over to the end, you can see it reads 0. And now I want to see how far in. This is as the one-way time delay. Here I think is where the fixture is basically ending. So it's about 97.7. Let's call it 100 picoseconds as the end of the fixture. I'm going to take this whole piece, build that transmission line model of it, de-embed it off, and just have the uniform part of that 34 ohm transmission line as what we see. And of course, we're going to do that on the left side, and we'll do that on the right side. So now we know in this very simple way how long the fixture is. It's 100 picoseconds from the beginning of the board. And we're going to de-embed, we're going to calculate that fixture model on both the left and the right side 100 picoseconds in from the end. Let's set that up and we'll de-embed that fixture. And the way we do that is accessing the gating tab over here. We will enable the de-embedding feature. We'll enable the de-embedding from both ports. If we want to peel, in other words, if we want to calculate the specific impedance of that fixture attached to that device under test, that's the in situ de-embedding part, then we select peeling. Otherwise, we can just take that time delay and assume it's a uniform 50 ohm or whatever impedance line that we want. So we can effectively extend the port. This is called port extension, any time delay into the structure that we want. If we also want to build the model for the specific impedance profile, that's where we use peeling. So we're going to peel from both ends, and we're going to use 100 picoseconds as the time delay from both ends. Now the wave pulsar 40IX is literally going to go in, build that little transmission line model, calculate the S parameters, calculate the T parameters, take the inverse, take the T parameters of the whole structure, multiply them all together, get the T parameters of just the device under test, convert that to S parameters, and then display it. And to see the difference, to see the impact, we're going to save the insertion loss and the return loss so we can see how much it's changed. So we're going to save a waveform. And the waveform that we're going to save is going to be first the return loss, that's register S1. So we're going to grab S1. We'll put that into memory 1 and we'll save. And now we also want to save the insertion loss. And the insertion loss is register S3. So we move S3 into memory location 2, and we'll save that. So here are the save values. Now I'm going to move them over here so that they're on the same screen. Now when I enable de-embedding and I recalculate, we'll see what we started with, but we'll also be able to compare that with the de-embedded insertion and return loss of just the 35 ohm structure. So let's recalculate. Part of having a deep toolbox means that we don't have to retake measurements. We take one measurement and then perform all the analysis we need to on that one measurement. So we'll recalculate, which is really doing the de-embedding. So all that matrix math and the inversion and the multiplying and the converting to T and S parameters all being done for us, and we're done. And now we see, and I'm gonna be selective in which waveforms that we look at just to make it a little easier to see what we've got. This is what we had before. This is no de-embedding. Let's take a look at what happened to the return loss after de-embedding. So we still see that, yeah, it's still a large value, but then again, we've got a 35 ohm transmission line here. And so of course we're going to get reflected signal. Let's take a look at the insertion loss. And before we do that, notice that we are above 10 dB in the low frequency region, below about 4 gigahertz or so. So we would expect to see some ripples in the insertion loss, but beyond about 4 gigahertz, the return losses below minus 10 dB probably are not going to see any ripples in the insertion loss. Let's take a look. And here's the insertion loss. And sure enough, we see the ripples and they drop off. And we see that here's the difference between without de-embedding and with de-embedding. You can see a very monotonic drop-off, what you'd expect to see. And then, of course, we're falling off a cliff because of the circular mode in the SMA connector. Now, there's one other thing that we're going to do. We've basically de-embedded the launches. So we don't have that large discontinuity at the launch anymore, but we have our 35 ohm line. Right now, we're looking at the S parameters of that 35 ohm line embedded in a 50 ohm environment, and that's why we have all these reflections. We're going to change the port impedance to match it to the 35 ohms for that device under test. So I'm going to change the port impedance to 34 ohms. We'll lock it in, and now we'll see what happens to those S parameters when we have the 35 ohm relatively uniform line embedded in a 35 ohm environment. So we recalculate. Wow, look how low the return loss is now. Here's minus 30 dB. We're below minus 30 dB up to the bandwidth of the connector, would dramatically improve the performance of what this interconnect would look like if it was in an impedance environment closer to the characteristic impedance of that transmission line. And here is that insertion loss, very smooth, very monotonic, again, until the bandwidth of the connector in this application. This is how we can look at other devices that aren't 50 ohms and look at them, how they would behave in other impedance environments. And all that is possible using this very simple in situ de-embedding technique and the port renormalization. These are two really important features that dramatically simplify how we can turn the raw measured data into useful information. And so in this video, I just wanted to give you a little flavor for a few of the important features that we have in the deep toolbox. We looked at this very simplified de-embedding technique with no reference structure, where we use the in situ de-embedding, and we looked at the port renormalization. In the next videos, we're going to take a look at, well, if we had the 2x through, then we can use that to get us the end of the location of the end of the fixture, and we'll look at using that de-embedded information about the channel without the fixtures adding artifacts, and we'll also look at using the de-embedded channel performance in a system simulation so we can translate the S parameter behavioral model into eye diagram performance and some of the jitter analysis.